What if I told you that everything we thought we knew about the universe just got flipped on its head? The James Webb Space Telescope, humanity's most powerful eye in the sky, has just made a discovery that's sending shockwaves through the world of physics. From time-bending galaxies to impossible structures in the early universe, the Webb telescope is not just rewriting textbooks, it's tearing them apart. If you're ready to dive into a mystery that challenges the very foundations of space and time, stay tuned, because what we're about to reveal will change how you see the cosmos forever. In its mission to look back in time, the James Webb Space Telescope peered into a region of space over 13 billion light-years away. What it found left scientists in awe: fully formed galaxies that existed just 300 million years after the Big Bang. According to our current understanding of cosmology, these galaxies simply shouldn't exist. The universe was supposed to be in a chaotic, formative state at that time. Galaxies take billions of years to form and stabilize, but Webb showed us mature, well-structured galaxies with star systems and disks already in place. This defies the lambda CDM model, the prevailing theory of cosmology. If these galaxies are real and not some observational error, then we're dealing with a universe that's evolved far faster than any model predicts. Is it possible our timeline of the universe is wrong? Or is there a missing ingredient in the cosmic recipe? Another stunning twist involves the distribution of mass in the universe. Using gravitational lensing, where massive objects bend light like a magnifying glass, Webb mapped out how matter clumps in deep space. What it found doesn't line up with the predictions made by dark matter models. In regions where we expected heavy concentrations of dark matter based on simulations, Webb found either less or significantly more. This throws a wrench into decades of research. For years, dark matter has been the invisible hand shaping galaxies and clusters. But Webb's data suggests our models might be missing something crucial. Are we misunderstanding how gravity behaves on cosmic scales? Or is dark matter something else entirely, something we haven't even imagined yet? This revelation forces us to reconsider Einstein's theories, Newton's laws, and everything in between. One of Webb's key features is its infrared capability, allowing it to see through cosmic dust and back in time like never before. But even more bizarre is how it has captured light from events that happened billions of years ago, which appear too bright. Quasars, black holes, and supernovae are appearing more luminous and energetic than models allow. Some of the earliest black holes in the universe are as massive as the ones we see today, which contradicts everything we know about black hole growth. How could a black hole form, feed, and evolve that quickly in the infant stages of the universe? This suggests that either we've grossly underestimated the mechanisms of matter collapse, or that something unknown is feeding these structures with unexplainable energy. For years, scientists have debated the Hubble tension, discrepancies in how fast the universe is expanding. The James Webb Telescope has added fuel to this fiery debate. New data shows a different rate of cosmic expansion when compared to previous measurements from the Hubble Space Telescope and other sources like the cosmic microwave background. This means the universe may be expanding faster or slower than we thought. Either way, the numbers don't align. One possible explanation? There might be an unknown force or field influencing cosmic inflation. Or perhaps dark energy itself, the mysterious force causing the expansion, is more complex than a constant. If this is true, we could be looking at the need for a new model of physics entirely, one that redefines our relationship with space and time itself. When Newton gave us gravity and Einstein gave us relativity, we thought we had the big ideas covered. But Webb's findings are nudging scientists toward a revolutionary path, what some are calling new physics. From unexplained particle behavior to cosmic structures we can't account for, this telescope may have cracked open a door we're not ready to walk through. There's now speculation about exotic forms of matter, alternate dimensions, and even multiverse theories gaining traction. If these observations continue, we may soon need to revise the standard model of particle physics, reshape how we teach cosmology, and rethink the origins of everything. The James Webb Space Telescope isn't just a machine, It's a messenger, delivering us truths that challenge the very core of what we know. As Webb mapped deeper into the early universe, something astonishing emerged. Complex, web-like structures connecting galaxies, called the cosmic web, appearing far earlier than expected. These filaments of gas, dust, and dark matter are the universe's skeleton. According to standard models, such large-scale formations shouldn't exist this soon after the Big Bang. Their presence suggests a more rapid, coherent organization of matter than our simulations have ever predicted. How could such massive structures evolve so early without enough time or gravity to organize them? Either our understanding of matter distribution is incomplete, or the universe may have evolved under rules far different than we've theorized. This discovery hints at something more intelligent, more ordered than random chaos. Could this be a signature of deeper natural laws yet to be discovered? Webb has detected stars in the early universe that appear to be population 3 stars, the very first generation of stars made almost entirely of hydrogen and helium. But some of them are much larger, brighter, and older looking than they should be. These stars are supposed to burn fast and die young, leaving behind black holes or exploding as supernova. Instead, Webb is seeing stars that have somehow survived or matured in a fraction of the time. This challenges everything we know about stellar evolution. It raises key questions. Did stars evolve faster in the early universe? Or are we missing crucial steps in how they form and burn? Either way, our stellar models may be too simplistic for the complex reality that Webb is now uncovering. Using its powerful infrared imaging, Webb has captured unusual infrared echoes that don't match any known astrophysical source. These echoes appear as concentric rings of radiation expanding across deep space, like ripples in a cosmic pond. What caused them? Some scientists believe they might be signatures of unknown energy bursts or exotic objects like boson stars or even wormholes. Others theorize they might be signals from ancient cosmic collisions. The disturbing possibility? These might be remnants of events that defy known physics, perhaps even messages from the structure of space-time itself. Until we can explain them, they remain as haunting reminders of how little we know. Webb has revealed galaxies with bizarre shapes, elongated spirals, irregular bars, and twisted arcs, in timeframes far earlier than models allow. Galaxy formation is thought to follow an orderly path, from chaotic clumps to elegant spirals. But what Webb is showing us is more like artistic chaos, galaxies that look fully developed with mature patterns only a few 100 million years after the Big Bang. This suggests two things. Either galaxies evolve in ways we don't yet understand, or the rules of galactic formation are much more flexible than we've believed. Could quantum forces or unknown gravitational interactions be playing a role here? One of Webb's most surprising revelations is the detection of heavier elements like carbon, oxygen, and even iron in galaxies that are too young to have produced them. These elements are formed inside stars and released during supernovae, which take billions of years. So how did they appear so early? Are stars producing elements faster, or are there unknown sources, like exotic stellar processes, that speed up nucleosynthesis? This discovery could mean the basic chemical evolution of the universe happened on a much faster scale than we ever imagined. Webb's ultra-deep field observations have uncovered light distortions where nothing is visible, no stars, no galaxies, no clouds. Yet light from background objects is bending, as if something massive were there. Scientists suspect these could be dark galaxies, structures made almost entirely of dark matter, emitting no visible or infrared light. If confirmed, this would be the first direct evidence of such entities. But it also means there's a vast, invisible architecture to the universe we've only begun to detect. Another baffling discovery: supermassive black holes, some with the mass of 1 billion suns, forming just a few 100 million years after the Big Bang. According to current theories, such behemoths should take billions of years to accumulate that much mass. Yet Webb sees them already anchored at the centers of young galaxies. This hints at either radically fast feeding mechanisms or unknown seed black holes from the Big Bang era. Are we missing an entire chapter in black hole physics? Webb has recorded energy patterns that don't match any known objects. No stars, no black holes, no galaxies. Some of these signals show rhythmic pulsations or sudden bursts of energy with no clear source. While some believe these might be exotic stars or collapsing cosmic strings, others entertain the possibility of advanced phenomena like artificial megastructures or energy harvesting systems. While speculative, these energy signatures remain a puzzle that refuses to fit into existing frameworks. Among the most controversial findings are curved light distortions and time-lagged reflections that some interpret as signs of primordial wormholes. These would be relics from the Big Bang, tunnels through space-time predicted by Einstein's equations but never observed. While it's too early to confirm, the patterns Webb sees mimic theoretical predictions with uncanny precision. If true, these wormholes might allow light, or even matter, to travel vast distances instantly. Webb has observed galaxies that do not display the expected redshift time dilation. In theory, as light travels through expanding space, its frequency stretches, making distant galaxies appear older and slower. But some galaxies are behaving as if they're not aging correctly, showing inconsistent time dilation. This might indicate that cosmic expansion varies by region, or that time itself doesn't flow uniformly across the universe. While Webb doesn't directly detect gravity, its high-resolution imaging has revealed gravitational effects that may hint at quantum-scale fluctuations, something predicted by theories of quantum gravity. Small inconsistencies in gravitational lensing, jittery light paths, and fluctuations in cosmic background radiation could be signs that space-time is grainy, not smooth. If confirmed, this would bring us closer to uniting quantum mechanics with general relativity, one of physics' greatest goals. In several regions, Webb has detected shock waves and remnants of ancient collisions between massive galaxy clusters. These epic crashes seem to have occurred far earlier than our models allow. The energy released in such events would have reshaped local physics, perhaps even triggering the formation of early galaxies and black holes. The timing of these events suggests a hyperactive early universe, far more violent and dynamic than previously thought. Webb's spectroscopy tools have examined exoplanets orbiting distant stars and found atmospheric signatures that boggle the mind. Some planets show carbon monoxide and methane combinations that shouldn't be stable. Others contain hints of water vapor in regions too hot for liquid water to exist. These anomalies raise the question, are we seeing unknown atmospheric chemistry? Or could some of these signals be artificial in origin? Webb has uncovered vibrant stellar nurseries, regions where stars are born, in places previously believed to be barren voids. These star-forming regions exist in intergalactic space, far from galaxies. Their existence challenges our understanding of how stars form, suggesting that isolated star creation may be more common, or governed by unknown forces that work outside traditional galactic environments. One of the most tantalizing interpretations of Webb's data is the statistical noise in cosmic background radiation. Some scientists argue that this could be gravitational bleed-over from parallel universes. If the multiverse exists, their gravity might faintly tug on ours. Webb's ultra-sensitive instruments may have detected the faintest hints of this cosmic interaction. While highly theoretical, the possibility is thrilling. Could Webb be the first observatory to find indirect evidence of other universes? With only a fraction of its mission complete, the James Webb Space Telescope has already overturned pillars of modern physics. But its most profound discoveries may still lie ahead. From probing the atmospheres of Earth-like exoplanets to capturing the birth of the first stars, Webb is poised to answer questions we haven't even thought to ask. As it continues scanning the cosmos, we may not just rewrite textbooks, we might have to write entirely new ones. Webb has surveyed multiple regions where star clusters were predicted based on Hubble and radio telescope data, but what it found was nothing. Instead of the expected stellar fields, Webb detected eerie silences, no light, no movement, no infrared signatures. These void pockets suggest there may be undiscovered cosmic phenomena that suppress star formation entirely. Could these areas be affected by exotic energy fields? Or are we seeing the footprints of phenomena like antimatter clouds or dark energy concentration zones? The absence of data is, paradoxically, the loudest clue yet that something extraordinary might be hiding in the darkness. In several galaxies, Webb observed gravitational distortions, stars and gas pulled into long arcs, much like the effect of a close gravitational flyby. The problem? There's no nearby galaxy or massive object to account for these tidal effects. It's as if invisible forces are reshaping galaxies without a source. One theory posits undetected compact dark matter halos, while others entertain more radical ideas, such as temporary wormholes or even objects from parallel dimensions brushing against our own. Whatever the cause, it's clear that something unseen is interacting with visible matter on a massive scale. One of the most profound assumptions in cosmology is that the universe has no overall spin. It's isotropic. But Webb's deep observations hint at a subtle rotational bias in the distribution of early galaxies. If true, this means the universe as a whole might have angular momentum, a concept that could overturn general relativity's foundational assumptions. A spinning universe implies a preferred direction in spacetime and could mean our cosmic origin was far more structured than the Big Bang theory allows. Some of Webb's gravitational lensing measurements contain odd harmonics, resonant patterns that don't match conventional models. A few leading-edge theorists suggest these could be gravitational echoes from higher dimensional structures collapsing into our three-dimensional universe. According to string theory and M theory, multiple dimensions existed at the birth of the universe but quickly compactified. These echoes could be evidence that those dimensions once left a real, measurable imprint, confirming a cornerstone of modern theoretical physics. Webb has found compact star clusters in the early universe that are so dense, they're challenging the limits of how stars can physically exist together. These hyperdense clusters pack millions of stars into areas only a few light years across. Our models say radiation pressure and gravitational chaos should tear these clusters apart. But they're not only surviving, they're thriving. These cosmic furnaces may be where supermassive black holes were born. If confirmed, these dense clusters could be the missing link in explaining how massive structures form so early. Webb's ultra-sensitive instruments have detected rogue objects, planets and stellar remnants floating freely in intergalactic space. Not bound to any galaxy or star system, these nomad objects defy standard formation theories. How did they get there? Were they ejected from galaxies during ancient collisions? Or are we seeing a whole new method of planetary formation, one that doesn't require stars at all? These findings could redefine how common planets really are and how they might support life in the most unexpected places. When analyzing the most ancient light in the universe, Webb revealed an unsettling symmetry. The cosmic microwave background, CMB, appears to have mirrored regions, patterns that suggest an unnatural level of order. Some theorists now propose that the universe may have undergone a phase of mirrored inflation, possibly due to interactions with parallel branes in higher dimensional space. If this holds up, it could be the first evidence that our universe is one of many, formed not from chaos, but from a cosmic blueprint. Magnetic fields play a vital role in shaping galaxies, stars, and even the behavior of cosmic dust. But Webb has detected strong magnetic influences in galaxies far too young to have generated them naturally. This suggests that magnetism may have existed from the very beginning, embedded in the universe like gravity and light. Such a discovery could indicate a new fundamental force or reveal magnetism as a guiding principle in early cosmic structure formation. Webb's redshift data, used to calculate distances and the age of light, has revealed inconsistencies when compared to other measurements. Some galaxies appear older or younger than their redshift values suggest. This silent rebellion against cosmological redshift could mean that either the expansion of the universe isn't uniform or our very method of measuring distance is flawed.
If redshift isn't the gold standard we thought, every distance in the universe might be up for debate.
In a strange twist, Webb's observation of pulsar-like emissions in dense stellar regions shows energy fluctuations in predictable, repeating cycles without using energy, similar to the behavior of time crystals, a newly theorized phase of matter. These structures maintain motion without energy input, defying classical thermodynamics.
If such behaviors exist in astrophysical environments, it opens the door to exotic states of matter operating in extreme conditions, far beyond anything ever imagined. Webb has also detected ultra-cold, dark regions between stars where light seems to vanish, far colder than cosmic background temperatures. These voids are unusually stable and seem to absorb radiation. Some researchers believe they may be proto-voids of dark energy or even signs of localized quantum fields suppressing activity.
What's most eerie? These voids are not empty. They may contain something, but we don't yet know what. In several parts of deep space, Webb has recorded gravitational lensing effects, where there is no detectable mass, no galaxy, no dark matter, no visible explanation. This has puzzled scientists deeply. Could we be witnessing phantom gravity, a sign of quantum fluctuations, or perhaps relics of gravitational waves from previous universes?
If gravity can act without mass, then a whole new chapter in physics is waiting to be written. Webb's most sensitive detectors are picking up photons from ancient galaxies arriving out of sequence, some arriving too early, others too late compared to expected values. This isn't just measurement error. It suggests something may be interfering with light itself as it travels. Could this be due to fluctuations in the structure of spacetime?